All right, so in this video, we're going to look at how to calculate the mass of a volume, and we're going to do it in several coordinate systems, but we're going to start with rectangular coordinates. Now, like in the two-dimensional case, essentially, we're going to integrate the density function over the volume region. So the density function is going to be the function that we're going to integrate over, and then our limits of integration are going to be dependent upon our plane. Now, recall that to set up our limits of integration, our initial one, since we're bounded by the coordinate planes, our top function is going to be this plane, and our bottom function in the z coordinate is going to be 0 because we're in the first octant. Now, from there, we are then going to set z equal to 0 to find out where the line is bounded in the plane, in the two-dimensional xy plane. Set z equal to 0, and then solve for y. And when we do that, we get 0, because we're in the first octant, and then the line in that plane, that where the plane intersects with the xy plane, is 6 minus 2x. And then finally, we take that equation, we set y equal to 0, and we find out what the limit in x is. And again, that's going to be our 0 to 3. This is our density function, x, y, z, and then we're integrating dz, dy, dx, which is sort of standard. Now, once we have our integral set up, then we have to do our antiderivatives. And this is where things get a little tedious, but they're relatively straightforward. Our x, y, z, we integrate the z, we get 1/2 z squared. And then we plug in our 12 minus 4x minus 2y, and the 0, of course, disappears. Now, because we're squaring that, we get, you have to FOIL this out. It gets kind of messy because you have to do 12 times 12, and then 12 times the negative 4x, and then 12 times negative 2, and then negative 4 times 12, and then negative 4x times 12, and then negative 4x times negative 4x, and then negative 4x times negative 2y. And then you do that again, you're foiling negative 2y times 12, and negative 2y times negative 4x, and negative 2y times negative 2y. And what you end up with is this crazy expression. 16x squared is from this component squared. 4y squared is from this component squared. 12 squared gives us this. But then these two together are going to give us negative 48 x, but then there's two of them because you're doing it the one way and then the other way. And then same thing for this one. This is 12 times 2y. It's 24, but there's two of them, so that's negative 48. And then you have two of these, you get 8xy, and then there's two of them, and so you get 16xy. And once you have that all squared out, and I pulled out the 1/2, then although these are all even, you could distribute it through. Then you distribute your xy into this crazy expression, and then you proceed to the next set of integrations, which is the y dy right here. So our y becomes 1/2 y squared. And so we have some simplification happening here. And then we have our y squared becomes 1/3 y cubed, and then the y 1/2 y squared, and then the y cubed becomes 1/4 y to the 4th, and y squared is 1/3 y cubed, but the 24 and the 3 cancel. And then again, another y cubed, but then 72 divided by a y squared, and then that divides by 2. And then the 6 minus 2x, you have to plug that in to all of your y's. And again, this is going to be, there's a lot of algebra that I'm omitting from this example, because you're going to have to do, when you plug into this y squared, 6 minus 2x, you're going to again have to FOIL 36 minus 6 times 2 is 12, 24x in the middle, and then plus 4x squared at the end. And then you're going to have to do that cube here and the square and the 4th. and the y cubed and the y squared, all of that, you get a big mess. And when you simplify everything, you should end up with a simplified expression that is now going, and again, this I've omitted so many steps here. You're going to end up with a simplified expression that has only x's left in it. And finally, then you can integrate your x component, and what you end up with in the end, in assuming I didn't make any algebra mistakes, which is possible. I am only human. I ended up with 324 over 5. Now you can try to verify some of these results by using integration software like MATLAB or Maple, or I have a TI-92 that I will sometimes drag out for these purposes. But once you get through all of the tedious algebra, you should end up with a constant as your answer. Again, I mean, that's setting these up is not that difficult. Once you understand how to set up triple integrals, that's fine. It's integrating in these kinds of problems. It's just the tedious algebra, because you're plugging in, you know, this plane that has 3 terms in it. And then depending on what your density function is, you may have a lot of squaring to do or cubing to do. And then when you do that for when you start with the plane and you do that for the second component, again, unless you have a very simple density function, you're going to end up having to do that again. And again, get even more crazy algebra. And then finally, you'll get down to a constant. Again, how difficult or simple this is to do the actual integration for is going to depend a great deal on the density function and the specifics of the plane that you're integrating, or whatever the function is that you're integrating over. Now let's look at a similar example for cylindrical coordinates. Now cylindrical coordinates, recall, is essentially x and y get converted to polar, and then we have z as our third dimension. In this case, we're going to find the mass of a volume bounded by the xy plane and the surface of this upside down paraboloid 16 minus x squared minus y squared. And the density function is going to be given by this thing that looks like a cone, but when we convert to cylindrical, will just be r. Now we're intersecting with the plane, which is z equals 0, and that paraboloid is a circle when it intersects the plane. So cylindrical coordinates is appropriate. Our x squared minus y squared becomes minus r squared. And as I mentioned, our density function just becomes r. And then our dv, our volume component, dz, dx, dy, becomes r dz, dr, d theta. Our density function is r. And then for the z component of our triple integral, we're going from 0 to the paraboloid. In the plane, our intersection of this paraboloid with the plane is a circle of radius 4. So we're going from 0 to 4 in r, and then 0 to 2 pi if we're going all the way around. Now, we can combine our r and our r to get r squared. And then we integrate z first. There is no z here, so we just plug in a z. And then we replace the z with the 16 minus r squared. And that gets multiplied by r squared that was already there. And so we end up with 16r squared minus r to the 4th. And then we can integrate with r. And we get this, and we plug in 4. And then finally, after simplifying that, we integrate in theta. There is no theta, so we just multiply by 2 pi, and we end up with this. And again, in cylindrical and of course in spherical coordinates, it is not uncommon at all to end up with a volume that depends on pi. And then finally, we'll also look at one in spherical coordinates. Now, where things can get a little bit complicated is that rho is typically the name we give to the density function, but rho here is also a variable, the distance from the origin in 3 dimensions. So it's important to try not to confuse the two. You may want to provide some extra notation, like the density maybe being rho sub d or something like that, just so that you can keep track of which rho is which. We're not really in math supposed to use rho for 2 different things. This is going to go away as soon as we start plugging things in, but it's important when you're setting up the problem that you can keep the rho for the density function and the rho for the variable separate and distinct in your mind. Now we're going to find the total mass of just the sphere of rho equals 3 in the first octant. And then we're going to use the density function rho cosine phi. So essentially, rho cosine phi is the z coordinate. So this density is changing with respect to the z coordinate. Now, the density function goes into our integral, and then our dv, our dz, dy, dx gets translated into spherical coordinates as rho squared sine phi, d rho, d theta, d phi, and or rho d phi, d theta, whichever order you want to integrate in. Again, we'll have to multiply our 2 rows together to get rho cubed, and we'll have a cosine phi and a sine phi to integrate when we get there. Our limits of integration, since we're in a sphere, are 0 to 3. And then because we're in the first octant, we're going from 0 to pi over 2 and 0 to pi over 2 in both theta and phi. We integrate rho cubed to get 1/4 rho to the 4th. In this example, there is no like k in the density function. If there was, you can move it outside and not have to deal with it for the integration. Just put it back when you're done. 1/4 rho to the 4th, and we plug in our 0 to 3, and that simplifies to 81 over 4. And then we have to deal with our theta integration. Now, the theta integration, there are no thetas in this expression, and so we would end up just multiplying by pi over 2 in this case. So that's where we get this. I think this should actually be 81 pi over 8. And then little typos, and that's why we walk through them. And then to integrate the cosine phi, sine phi, you choose one of these to be your u variable, and then you do your substitution, and you get 1/2 u squared. And again, I think this should be an 8, and that would make this 81 pi over 16. And when you plug in the pi over 2, you just get 1. And so you get your final answer, which again, because of this, I think should actually be 81 pi over 16. It's always a good idea to double check your work. But yeah, again, we're only human.